everyone, welcome to 11th session of number systems on playlist of quantitative aptitude for CAT and OMETs. So far we have covered sum of total number of factorials and several other things similar to that. Now in the last session we have taken a glimpse on how to calculate the IGP of a number in a particular factorial. So let's try a new example in that case. So this time we have a number 10. And for this we have to find its factorial in the 128 factorial. Its IGP would be normal procedure. You would be doing like this. You will keep finding the quotients by dividing 128 by 10 subsequently. But have any of you even noticed that even though you can get 13 here, method itself is not wrong, but the approach you are doing is wrong. Why? Because 10 is not a prime number. And as I had said at the first practice session itself, that this method is applicable only for prime numbers. So you cannot directly go around doing this with 10. But we do know for a fact that 10 is a combination of primes 2 into 5, right? It is a multiplication of both of them. So what we can do is we can find IGP of these two numbers in 128 factorial, and that's what we are going to do. So first we will find for 2, and similarly we will repeat the same procedure for 5, and you will be left with IGP of 127 and 31 respectively. And also I don't even need to say this, you might have noticed when I was adding up all the quotients for 2, I directly wrote 64 plus 63. This is not something I calculated in calculator, it was directly from visual, and you also can try that, because from here you can directly see that 64 and 8 they make a pair, 32 and 8 they make a pair, 16 and 4 make a pair, and similarly you can also find other pairs. So that is a smart way of doing this. So 64 I wrote directly as it is, and 32 and 8 made up 40, 16 plus 4 20, and then you are left with 3. So 63 you can directly get and add it up. So this is a smart trick you should also always implement, so you can get a better speed at doing mathematics in the mind itself without using paper and pen in exam, because it is always much faster. And yeah, though we are having 127 as the IGP of 2, but we only have 31 IGP of 5. It is just like a case of having a complete set of a bottle. You may have 127 caps, but the actual bottle, if you are only having 31, what will you do with the surplus caps? They are useless, right? You can only make 31 complete bottles. So similarly, even though you have surplus in this 127, you can only use 31 of these to make a complete 10. That's why our final answer would be 31. Now, with that straight out of the point, let's try again. This time for 21, and for 21 we directly know it's a multiple of 7 and 3. So we'll repeat the procedure, and this time around I am only going to find the IGP of 7, and that will come to 45, and that is going to be my answer. Now some of you may argue, why didn't we find for 3? Because it is a very common sense. The greater a number is, the less frequently it will occur in a series. If you take 2, it will occur at every alternate instance, like at 4, at 6, and similar things. Similarly, as the number keeps on increasing, its frequency gets reduced. That's why no matter what the case, the higher prime will always have the lower IGP. That's why I don't even need to bother about 3, because I know for a fact that in 280 factorial, the IGP of 3 is going to be definitely higher than 7. But as I said in the previous example, you may have surplus caps, but you need to make a complete bottle. You need to make complete 21. That's why only 45 is our valid answer. So that's one other trick you can use. Whenever you directly get a combination of such primes, you can directly go for the higher number and find the IGP of that. And that will be the IGP of the overall number, composite number that you are planning to find. Now, let's make it a bit more tricky this time. This time we are going to find for 56. Now, 56 itself is not a combination of directly primes, but a prime and an exponent of a prime. As you can see, it is 2 cube. So logically, if you think 2 cube is 8, which is greater than 7. So should we try IGP of 8? Let's try that. So I cannot directly find for 8, but I can find for 2. And again, in a smart way, if you try to sum it up, you will be ending up with 375 plus 22. So that will be 397. But this is IGP of 2. We are looking for IGP of 8. And if you might have noticed, 8 is nothing but 2 cube. So you will directly divide this IGP of 2 by 3. which is the power of exponent for making 8. So that will be 132. So 132 is the IGP of 8. Now, as per the previous logic, is this the correct answer? No, that's not the case. If you try again for 7, the same method, you will be left with 66. As you can see, here the logic didn't come around. Now, you may argue that actually 2 is lower. If you ignore the power, 2 is lower. So that's why 7 was the bigger this time. But I will show you another example that this is not the case. Whenever power or exponent is involved in a composite numbers multiple, then there's no shortcut. You directly have to find by trial and error. But in any case, in this case, our answer would be 66. Now, I will just for your peace of mind show you another example using 40 and 80 in 250 factorial. Here I will show you example how the scale can vary. So I have intentionally chosen this number. As you can see, power is 3 and 4, just this is the only difference. So I will only find the IGP of 2 ones and I will find 40 and 80 from itself. So again a smart summation and you will end up with total IGP of 244 for 250 factorial. For 8 I will divide it by 3 and for finding 16 I will divide this number by 4. Now I will be ending up with 81.33 and 61. So as I said, there is no need for surplus. You'd round it off to lower value. Even if it was 81.69, 81.7, even 81.99, you will still go with 81, which is the lower rounded off value. So yeah, for 40 and 80, IGP would be 81 and 61 respectively. Now, if I do the same thing for 5, I'll be left with 62. Interestingly, this IGP is between 40 and 80 because IGP of 40 would be definitely 62 because 81 and 62 lower number is our combination that we need, but for 80 it will become 61 because I may have an extra 5 but I don't have a 2 to spare for making again 80. So in this case it is a clear example that whenever the composite number given to you has exponent of prime in it, you have to try all the IGPs for primes. Yeah, but definitely if there is no exponent involved in the multiple, then you can directly go for the higher number. That is a surefire trick that you can use. With this, I am pretty sure you guys are clear. Now let's take it up a notch. So if IGP of 7 in n factorial is 6, how many possible values can n take? This is a CAT question and it has also come in Z once. So do pay attention to it. And don't worry, though it may sound tricky, it's very simple. First understand that what it is asking. It is just simply saying there is an unknown n whose factorial we are having, and in that value, if I am trying to find IGP of 7, it will be 6. So how many such number exist in which IGP of 7 is 6? That's what it is asking us. Now, to be very frank, at first, if you don't know anything about it, you may try random things. So that's what I am also going to do. I am simply multiplying the given two numbers, that is 7 and 6. So I will left with 42. Now if I try to find IGP of 7 in 42, I directly got my answer. It is 6. Quite simple, right? Now if you keep trying like 43, 44, eventually like 49, that's where a new 7 is added, right, in the factorial. So here you will notice that till 42 to 49, like till 48 to be more precise, all the numbers will have IGP of 7 as 6. But once you come at 49, it will directly become 8. So 7 cannot have IGP of itself. So for any prime number, a prime number in any n factorial will never have its own power, greatest power. So that's a thumb rule. And yeah, other thing you can conclude from this, that number will either have the prime number itself as the count of possibilities in which it can exist. Like the main question was, we have to find the possibilities of n, right? So how many n are there? It is 42, 43, 44, 45, 46, 47 and 48. These are 7 numbers. Why not 8? Because once you go beyond that, a new 7 is introduced. So the power directly changes. Similar is the case for any prime number. The number of times, the frequency, that in itself causes a change in the IGP. That's why the answer would always either be the number itself or 0. No need to think about it. Either it exists or it does not exist. If it exists, then it is the number itself. Quite simple, right? So to just get it through your head, let's try another example. So if IGP of 5 in p factorial is 5. How many values can p have? So these were the options that were given in the examination. Straight ahead, many students went for cannot be determined, which is incorrect, because it is indeed determinable that pi cannot have its own power. So the correct answer would be 0. As I said, if it existed, then the answer would have been 5. P can have 5 values, but it does not exist. So the answer is 0. Nothing rocket science, right? Now, moving on. So IGP of 11 in a p factorial is 13. How many values can p have? Again, quite simple. But this time I have intentionally taken it. Can you find what are the values that p is going to have? Just try it once. So 11 to 13, you will be left with 143. Now if you try to do the same method that I showed you in the first example, you will end up with 14. But I wanted IGP 13. I got 1 extra na. So I will multiply with a lower number. How much lower? Well, how much extra I got? I got 1 extra. So I will multiply with 1 lower. So this time 11 into 12. And I will get my answer that, yeah, 132 is the number that I am looking for. So again, from 132 till 142. All these numbers, including 132 itself, are having IGP of 11 as 13. So again, they are 11 numbers. So yeah, my answer would be 11. As I said, either it will be 11, that is the number itself for which we are finding the IGP, or either it will be 0. But the reason for showing you this, why we calculated this 11 into 13, 11 into 12 was because you need to know how to find these values. Because not always CAT and ZAT will give you such easy questions. The real type of questions that are more frequent will come now. So here, now the nature of question has been tweaked slightly. Here again the starting phrase would be same, that in p factorial IGP of 13 is 56. But we are not interested in finding how many values p can have. What we are interested is, if this number p factorial, what is the IGP of 11 in this same number? What is the greatest power? And mind well, though I have written IGP here, IGP itself means the greatest power. Keep that in mind while you try to solve it. Now, as I demonstrated earlier, we will try to find the number p first. So, as usual, 13 into 56, 728. I will try to find the quotients, consecutive division. I will be left with 60. Again, I was 4 steps ahead of what I wanted. So, I will multiply with a 4 steps lower number. That is 56 minus 4, 50. And yeah, I got my number 676. But if I directly go for finding IGP of 11 in 676, don't you think something is amiss here? Right. If some of you might have guessed, this is just one number where IGP is 56. There are certainly 12 other numbers who will have IGP of 13 as 56. That's why we have to take the greatest number, because we have to find the greatest power of 11. So this series will continue till the next multiple of 13, that is 13 times 53, which will come to 689. So 689 is the number for which I will going to do the operation of 11 to find the IGP, and I will be left with 72. I think that is pretty clear at what you have to look around for. Now, if you see in the options, they have smartly given the same values that we have found, right? 60, 56 and 72. So if you guys might have just stopped at the second step itself, you might have taken the wrong answer. Now you know what you need to do, right? You have to find the highest P, and in that you have to find the IGP of the given number. So it's a two-step process. Keep that in mind whenever you see such a question in examinations again. So with that said, let's meet again in the next session. Thank you. I hope you guys enjoyed the session.